Yes. Good morning, everybody. And today we will give the one more and the procedure and how to find the basis for our space. If we have the sum and the vectors, we claim that and find the subset of this set such that and this one should be basis for our space. It's okay, our space. And they use a different color, will we? Yes. And here. Take this set S. It's okay. Our set contains and the k vector. It's okay. K vector. And and here look at this one. This one is S. It's okay. Contain V1, V2, VK. VK. It's okay. This one. So and our space are to do n. Let's give this and the procedure and for finding the subset of S, and means and find for example this one is a subset of S. This one is called B, and but such that and this B is a basis for and the W is span S. Span S, what does it mean span S? Span S means take the R vector in S and generate and use the linear combination and the definition, and so we obtain this some linear combination. For example, 1 over 2 V1 plus 2 V2, and for example 3 V3 plus and plus 10 VK, another and the linear combination. We know that and the all linear combination give a vector in Rn, and these and the all look at the all linear combination, and this set is called span S. It's okay. Span S contains all linear combination of vectors in S. It's okay. So this one is a subspace and space, and our aim is to find the subspace of the and these subspace. It's okay. Find the basis for this subspace. How to find? And let's give this step. Step 1. It's okay. Our aim is to catch the B basis, and for span S. It's okay. So for span S, first one, and write and construct the matrix A, and such that this matrix, how to construct? Write A. It's okay. Write A, and write all vectors in S, and the first column will be first vector V1. The second column, second vector, and VK. So we obtain and the matrix and this and the, what's the dimension, and it contains k vector. So dimension k and by the number of yes rows and the n, because our space and the R to the n, our vector in Rn is okay, n by k matrix. This one. The second step, reduce this matrix to the row echelon form, and means use the elementary row operation, and we get another matrix, but this one should be in row echelon form. Row echelon form, it is enough to say that. It's okay, we know, and this one. So we obtain and the same method use the and we know that use the and sorry, not the here. Sorry, and they take the A and they apply the elementary row operation. We get the and the new matrix in the row echelon form, and means and we have and the 1 1 1 and to the right and the left and this one, and these parts 0 0. It's okay, row echelon form. So look at this matrix, and so write the corresponding vectors. And these vectors in the basis should be in the basis, and which vector corresponding to the columns containing leading 1. So means, for example, this one is 1, this one is 1, this one is 1. It's okay. So look at this, and this one is V1, V2, this one is V2, 10, for example. So means other and the 0, 0, 0 here, and means all bases and our bases contains only V1, V2, V10. It's okay? So to understand this one, let's give the example. It's okay? Let's give this example. And take this set, and the question here, find the subset of S such that, and this one should be basis for span S. It's okay? Span S. And so S here, span S, this one is a subspace. This one R space Rn. It's okay? And the first one, construct the matrix A. How to construct? This one is V1, V2, V3, V4, V5, and V6. And we have the 6 vectors here. Write the matrix here. V1 here. It's okay. And V3 and the third column. And this one is the V2 and V6. It's okay, this one. So write the construct our matrix, and then apply the elementary row operation to get reduced row echelon form. Sorry, not reduce. Row, it is enough. It's okay. So look at this one, and it is easy to get under this one. It's okay. And consider this step, and then we obtain the row echelon form. Look at this one. This one is leading one. This one is leading one. This one is leading one. So look at this one. This one is V1, V2. This one, this leading one about to V4. So means our basis contains V1, V2, V5. And what is this one? Not take this one. This one is the column, but take V1. V1 means, yes, this one, V1, V2, V5. It's okay. So means, and we claim that, and this one is a basis for span S. We claim that, and take the only, and this vector, this one and this one means, and this one is, we can ignore this one because this vector is generating by using the V1, V2, and V5, and this one and this one, and not linearly independent, and delete the linearly dependent vector, and we obtain choose a vector such that linearly independent should be. It's okay. Any question? Okay, no question. Now, yes, let's give the important and the subject eigenvalues and eigenvectors. Is okay? So, what does it mean under this one? And they take and here, be careful. Our matrix should be square matrix. It's okay. To mention the eigenvalues and eigenvectors and all diagonalization, and they take the square matrix. It's okay. For example, n by n. It's okay. And the number lambda is okay here. Lambda is called the eigenvalue of the matrix A if there exists one non-zero vector x such that, and lambda and x satisfy this equation. It's okay, this equation. A is our matrix here, and the lambda is a scalar, and the lambda is called the eigenvalue, and the eigenvector x and x the same. This vector, non-zero, it is important, non-zero vector x. Our aim is to find x and lambda. And we have only our matrix A, and then look at this equation, which is the lambda here, and the scalar, and the lambda. X is a vector, non-zero vector. It's okay? And x is called the eigenvector of A associated with the eigenvalue lambda. It's okay? But important point, x should be non-zero. It's okay, non-zero. So, and the question, And how to find of course our aim is to find the eigenvalues and eigenvectors of the n matrix. Let's write here. It's okay. Our aim, and write R matrix first, n by n matrix. It's okay. N by n matrix. N by n matrix. What is the eigenvalue and eigenvector? Look at this equation. Ax is a lambda x. Our aim is to find lambda is a scalar, and this one called eigenvalue. And the x here, x, but x should be non-zero vector, and this one is vector, and it is called eigenvector of matrix A, the corresponding to the and these eigenvalue. It's okay, the corresponding eigenvector. Our aim is to find x and lambda, and equation 1, this one. So, and look at this equation. Our aim is to find the x here. Look at, for example, right here, x is 0. X is 0, always solution. Always solution. Look at, and this one, write 0 vector, 0, lambda 0 times. So we obtain 0, 0. Yes, x is 0, always solution, but our aim is to get the non-zero x. It's okay, non-zero x. So how to find? It's okay. And how to find? And rewrite this equation. Start with this one. Ax is lambda x. Our aim is to find x. It's okay. So, and lambda. And so rewrite this one. This one is an Ax, sorry. Ax and lambda x is 0. This one. It's okay. So, and what does it mean, this one? Our A is a matrix, X is a matrix, lambda is a scalar. So this one is A minus, or rewrite, but use this one, the same. But it is not important, but in the lecture notes, and this one is in another order, another order. And lambda x minus Ax, Ax is 0. So this one means, and right here, this one is true, this one not true. What is the reason? Lambda is a scalar. Scalar minus matrix undefined. It's okay. This one is not true. This one should be, be careful, lambda identity matrix. It's okay, this one. So our equation 1, and guess this equation. This one is if and only if. So, and find the x and lambda, and means find the x and lambda here. It's okay. So what does it mean, this one? A is a matrix. We know A, and the I is an identity matrix. Lambda is a scalar. So this one is a matrix. This one is a matrix. X is our aim is to find the x. So what does it mean? And the coefficient is a matrix here. This one is a matrix. This one is a vector x. Our aim is to find x. What does it mean, this one? This one means this one is a homogeneous system. Look at this one. This one is homogeneous system. Because right-hand side is 0, and this one is coefficient matrix, and they find the x. So our problem, find the eigenvalue, to find the eigenvalue and eigenvectors problem, and this problem can be transformed into this problem. Which problem? And solve the homogeneous system. So solve the homogeneous system, find the x. Our aim, find the vector x, non-zero vector. So our problem is find the homogeneous system, solve the homogeneous system, means we know that x is 0, always solution of the system, but our aim is to find the non-trivial solution. X is not 0. It's okay? So, and the question, and here, and our question, we know, and how to solve the any homogeneous system. How to solve? Write the augmented matrix, or And also here we know that A is a square matrix. A is a square matrix. Identity is the square matrix. So lambda I minus A is a square matrix. Square matrix. And so our aim is to find the non-zero solution, non-trivial solution. So, and the question, how to check that any homogeneous system has non-trivial solutions, if coefficient matrix square matrix. How to check that and it has a non-trivial solution or not? For example, look at the design is coefficient matrix B X is 0 homogeneous, and the B is the square matrix. Our aim is to find the non-zero solution. So how to check that? And this system has non-trivial solution or not? And here look at the coefficient matrix B and look at these determinant. Maybe this determinant 0, maybe not 0. Not 0. It's okay, not 0. If not 0, what does it mean? And it means there exists the inverse matrix. Our matrix invertible. It's okay, invertible. So means our matrix invertible means we can use the B inverse. Take our system. It's okay. Multiply by the B inverse. So we obtain X is 0. So what does it mean, this one? This one means if and the coefficient matrix, look at the determinant non-zero, invertible, so we obtain only trivial solution. And this one is unique solution. But here our aim is to get the non-trivial solution. So means the coefficient matrix determinant should be 0. It's okay. What is the condition? Any system but square coefficients here and has non-trivial solution and means and the determinant coefficient matrix of determinant should be 0. Let's come back our question. Our coefficient matrix, this one. Our aim is to catch the non-zero solution. So, and the coefficient matrix, this one, look at the determinant. Determinant should be 0. It's okay to catch the non-trivial solution. It's okay if there exists, then it means determinant should be non-zero. 0. Determinant should be 0. Sorry. It's okay. Our aim is to get the non-zero vector. What's the condition? Determinant 0. It's okay. Any question here? So our problem, find the lambda and x. We get the homogeneous system. We get non-zero solution, and the condition means determinant should be 0. This determinant is called the specific and an aim, and this one is called this part, and also look at this coefficient matrix. It's okay. This one is denoted by P lambda A, and this one is called characteristic. Sorry. This one is denoted by P lambda and the polynomial, and this one is called characteristic polynomial. And this one, if is equal, polynomial is equal 0 and is called characteristic equation. It's okay, characteristic equation. So let's come back. This one. It's okay. This one is same idea. Yes, characteristic polynomial. And this one is called the characteristic equation. Let's give an example to understand this concept. Take our matrix A. It's okay. And find the characteristic polynomial of A. It's okay. So, and construct the lambda I minus A. and means, what does it mean? I is a lambda I minus a. Lambda is a scalar. I is an identity matrix, and look at this one: 1 0 0 0 1 0 0 0 1, and minus a. Right here, a. It's okay. The sun is a. So, and the sun gives multiplied by lambda, and it's scalar, and so means, and multiply all entries by lambda, lambda 0 0, lambda, and minus a, this one. So, and take the determinant. It's okay. So we obtain this one, lambda minus, and the sun is 1 2 minus 1 1 0 1 4 minus 4 and the 5. So, and minus means multiplied by minus 1, and so we obtain minus 1, and the sign is plus, minus, minus, plus, minus, 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 plus, minus. It's okay, this one. Plus, and so the sign gives, yes, this one. Lambda minus 1, 0 minus 2 minus 2, 0 plus 1, 1. It's okay, this one. So we obtain this determinant. Yes. So our aim is to compute this determinant. So how to compute this determinant? Our aim, write this one and find the lambda. It's okay, lambda. So, and this one is 0, characteristic equation. So, and compute this determinant, how to compute, and our aim is to get lambda, and a is 3 by 3, and this polynomial, this one gives the polynomial of degree 3, and this one is equal 0, and means we obtain 3 value of lambda. It's okay. So we obtain 3 eigenvalues of A. It's okay. So, and depends on you, and take this one using the row and column expansion. So we obtain this polynomial. It's okay. And the polynomial of degree 3, and this one is the characteristic polynomial. It's okay. So how to find? Using the, and choose the one and the row or column using the row expansion, or another method, and look at this one. It's okay. And our aim is to catch the same entry and row or column. For example, and also our aim is to compute these determinants. We get and the more 0 entry. So look at this one, and take this row, multiply by 1, add to the second row, and so we obtain lambda minus 1 minus 1, lambda minus 2, minus 2 plus lambda minus 2, and then we get 0 here. So look at the second row now. It's okay. Here contains the common entries lambda minus 2, 0, and means this row contains lambda minus 2, and we know that, and this one if contains the same value, and right here lambda minus 2 1 1 0. Be careful, this one is determinant. If any matrix here is okay, and we get the lambda minus 2, and here means multiply all entry contains lambda minus 2. Otherwise, it is not possible to write the lambda minus 2 and the matrix. But determinant, it is enough only to get the to look to only one and one row or one column if contains the same value. So, and this one is, and right here lambda minus 2 times and this one. It's okay. Be careful because this one is determinant, not matrix. It's okay. And so we know that, and from the previous lecture, take any scalar. This one is scalar. It's okay. This one is scalar. Take any scalar k, multiply any matrix, and the scalar multiplication means all entry multiplied by this scalar. But determinant multiply by any scalar means choose any row or column, multiply only these entries and by k. It's okay. So, and look at this one and this matrix, the next determinant, this one. Our aim is to get the more zero. So use the and look at this one. We get one more zero in this row, and using the, for example, column operation, multiply by -1, add to the first row, first column. -2, -1, +2, and this one, we obtain lambda +1. -1 +1, 0, -4, -4, -8. This one and this one the same. It's okay. So now look at the second row, and second row contains only one non-zero entry. So using the second row expansion, so what's this one? And the delete and this row and column. Lambda -2. Entry here 1. Multiply by 1. And sign of position. Plus, minus, plus, +1. So, and we obtain and this determinant. So, what's this determinant? This determinant is 1. It's okay? So we obtain the characteristic polynomial. It's okay? That's one. This one gives lambda square -4 lambda +3, and we obtain the characteristic polynomial. And let's come back, and our matrix A is 3, 3 by 3, 3 by 3, and we obtain polynomial of degree 3. It's okay? And if this one is 0, and right, and so we obtain characteristic equation. Find the roots of the characteristic equation. So we obtain lambda 1, lambda 2, lambda 3 eigenvalues. It's okay. That's all. Yes. Any question? Okay. Let's give this theorem. This theorem, it is important. And what is the relation between the matrix A and an eigenvalue? Sometimes eigenvalue lambda is 0 if and only if our matrix A is singular. What does it mean singular? Singular means not invertible. So if we know the A is not invertible, so we know that and the eigenvalues and the 0 is an eigenvalue. Or we know that 0 is an eigenvalue, A is not invertible. It's okay. This one, it is important fact. Be careful. And sometimes we use this fact. It's okay. And the next and the theorem, how to find the eigenvalues. We know and this one eigenvalues, and the eigenvalues, the roots of the characteristic polynomial. Let's come back our question, and this one is polynomial. What's the characteristic equation? Characteristic equation, this polynomial is 0. Characteristic equation. Find the roots, so we obtain eigenvalues. It's okay, eigenvalues, yes. So, and here, take the same and the problem and the same matrix and this matrix. It's okay. And they find and they take the same matrix and they find the eigenvalues and eigenvectors. It's okay, of the matrix A. And here we obtain characteristic polynomial here. Yes, characteristic polynomial, this one. So now let's find the eigenvalues, means let's find the roots of the characteristic polynomial and find the vectors. It's okay, eigenvectors here. Let's Yes. Look at let's take the same matrix and let's find the eigenvalues. We know and I have to find this one. It's okay. Look at let's come back this step, and rewrite this part, lambda minus 2, and this one give lambda minus this one. What's the here? And so we obtain the other eigenvalues. We obtain under this one. It's okay. So fine. We have the all eigenvalues and the 2, 1, and 3, and the eigenvalues of A. It's okay. Eigenvalues of A. So the next step, find the corresponding eigenvector. And let's come back here. So, and our homogeneous system, this one, lambda I minus A, x is 0. So, and this one is called the characteristic equation. Find the lambda. Lambda is an eigenvalue, and x the corresponding eigenvector. So we have 3 eigenvalues. So means take the lambda 1. So we obtain 1 eigenvector x1. Take the lambda 2, we obtain x2. Lambda 3, we obtain x3. It's okay. Now, but first of all, we write here in the equation lambda 1, first eigenvalue. We obtain and the system. We obtain one system, homogeneous system. Solve this homogeneous system, find the x1. And then substitute here lambda 2, we obtain another system, homogeneous system, and to solve this system, we obtain the solution. This one gives the next eigenvector, and then this one, lambda 3, we obtain the last homogeneous system, and solve this homogeneous system, we obtain the last eigenvectors. It's okay. Now, let's apply then to this one. Lambda 1 is 2, and find the corresponding eigenvector. And right here, homogeneous system, write the lambda 1, and means, and write here 2, and find the x here, homogeneous system. And here, but be careful, and what's the, and this matrix, and this one. Take this one. Let's come back our problem here. Look at this one. Look at this one, and the coefficient matrix this one, determinant this one, this determinant is equal this one, this one, this one. But choose the coefficient matrix and solve the homogeneous system. Take the one of them. Which one? If take this one or this one and this one, it is natural. And take the first determinant. Otherwise, your solution, it is not true. It's okay, because take the different homogeneous system, not our homogeneous system. Be careful. It's okay. And take this one first of all. It's okay. Take the first determinant. So take this one coefficient matrix. It's okay. So substitute here. And right here, and the coefficient matrix this one, so substitute here lambda 2 right here, lambda 2. It's okay. Lambda 2 minus 1 1. Substitute is lambda is 2. We obtain this one coefficient matrix, but this one is homogeneous, so write 0 0 0. So solve this homogeneous system by using the elementary row operation. So we obtain, yes, this one. So what's the x? X is x is x1, x2, x3. It's okay? And here. So, and right here, x1, x2, x3. It's okay? Because, and what's here? And the lambda, and the lambda is 2. 2 times a minus a times x is this one. This one determined, substitute is 2. 2, 2 is the coefficient matrix. Write the x. x1, x2, x3 is 0. Homogeneous system. So what's this one? And yes, this one gives x1 minus 2, x2 plus x3 is 0. This one gives, yes, multiplication, minus x1 plus 2x2 minus x3 is 0. Last one, yes, minus 4x1 plus 4x2 minus 3x3 is 0. So we obtain homogeneous system, but we don't have to write this system. We know when this one. How to solve? Write the augmented matrix. So coefficient of x1, this one, so and this one and this one. How to find this one? We can ignore this part. It's okay. So we obtain, yes, the coefficient matrix, apply the elementary row operation, and then we obtain the solution. So solution here, yes, this one, x1 and x3, x2 and x3. Write the corresponding equation. This one gives x1 plus x3 over 2 is 0, and this one gives this one. So we get free variable. Which one free variable? There is no leading one x3. x3 free variable. Take the any real number, x3, and x1 is substitute, x3 is r, and so we obtain solution, but we obtain infinitely many solution here. Be careful. So this system, and this system has infinitely many solution. Our aim is to get the only one non-zero solution, because our aim is to get the non-zero solution. It's okay? Non-zero vector. So write here any value, but r should be non-zero. Because what is the reason? You have to write this one, because if take r is 0, this one is 0, this one is 0, this one is 0, so we obtain 0 vector. But our aim is to get the non-zero vector, because eigenvector should be non-zero. It's okay? So here you have to write, and the r should be non-zero. It's okay, this one, non-zero. So, and we get any, take the any real number, so we get infinitely many solutions. But choose one of them. Which one? Depends on you, but I think it will be better. Look at this side, be careful, and take the, our aim is to get the integer number. It's okay, integer number, and it should be, this one is the smallest one. Which one? And take r over 2, r over 4, and take the r is 4. R is 4. Our aim is to get the integer number, because the next and the next subject, diagonalization, it's okay, diagonalization, and it will be better to get the integers. It's okay. So, and take the 4 and substitute here, r is 4, substitute, and then we obtain this one, x minus 2, 1, 4. So this one is called eigenvector of A associated with the lambda is 2. Lambda 1 is and the 2 and x1. It's okay. But, and take, for example, take the r is use a different color. R is, for example, 8. R is 8, and this one is 4. This one is 2 multiply 2 to this one. So we obtain 2 and this one another vector. But compare this vector and this one and take this one multiply by 2, so we obtain this one. It's okay. So means this one depends on our vector. So our aim is to get the linearly independent eigenvector. So and cancel. So means we obtain the infinitely many solutions. Choose one of them. It will be enough, because what's the reason? The others are generated by using these vectors, okay? Because they take this vector multiply by any scalar, so we obtain other vectors. It's okay. Generate the other vectors. Any question here? No question. So, but here we have 3 eigenvalue. It's okay. 3 eigenvalue. Let's come back. And we have 3 eigenvalue here. This one is okay. So, and we take the other one, we obtain the corresponding eigenvector. Lambda is 3 and 1. This one, lambda is 1. It's okay. And substitute is lambda is 1 here. Which one? This one. And the substitute here, lambda is 1. So we obtain homogeneous system, and this one is the augmented matrix of the corresponding homogeneous system. And solve this system, write to augmented matrix, and we obtain this one, x1, x2, x3. So row echelon form, reduced row echelon form, write the corresponding equation and solve for this one. So we obtain no leading one about x3. x3 is free variable, but be careful, should be non-zero. It's okay. So, and look at this one. Our aim is to get the integer number, smallest one. So substitute r is 2. R is 2. We obtain minus 1. R is 2, 2, and 2. So we obtain under ds vector. It's okay. So and so we obtain corresponding eigenvector. Corresponding eigenvector, this one. So the last one, last eigenvalue, give the homogeneous system, this one, solve, and so we obtain last eigenvector x3. It's okay. This part is homework. It is easy to get the solution. It's okay. And any question about here? How to find the eigenvalues and eigenvectors, and we obtain the homogeneous system and solve the homogeneous system, and the solution is the corresponding eigenvector. It's okay. Now let's have a break and the 10 minutes, and then we give the diagonalization. It's okay. Diagonalization. Any question?